Welcome to this week's South American Geometry webinar. As usual, if you would like to subscribe to our mailing list, send the word webinar to the email or WhatsApp number on the chat. You'll find there as well the link to our calendar of scheduled talks for the rest of this year, as well as all previously recorded talks on our YouTube channel. There's no spamming on these mailing lists. You will strictly get announcements for upcoming seminars. We have an agenda all the way down to the first week of December. Then we're going to close shop for the South American summer and be back hopefully in February. So keep an eye on that. We're going to have as our closing invitee Simon Salomon telling us about geometric structure, mostly G2 geometry, but then coming back next year as well. So today, very happy to have Matheus Vieira here, guy who works in all the topics of interest of this seminar. Surprises me every month with different things. Today we're hearing about biharmonic hypersurfaces in hemispheres. So Matheus, we're doing 50 minutes. We stop at 5:02 for questions, if that's okay.
Okay.
Also, please be reminded that Matheus will not be able to see you. So if you want to ask a question, either interrupt him or post a question onto the chat. You have the floor, Matheus.
Okay. First, I would like to thank the organizers for the invitation to talk about this topic, which I'm interested. Very interesting topic. I will talk about a recent paper which is on arXiv, studying biharmonic hypersurfaces in hemispheres. I will begin with a review of biharmonicity, some previous results, and then I will try to give an idea of the proof of the main theorem. Okay. So first, a quick review about harmonic maps and minimal hypersurface. So suppose we have a map between Riemann manifolds, a map P. Then we say that this map is harmonic if it is a critical point of the following functional: if E of phi equal to the integral of the exterior derivative of phi squared. So this is called the energy map. So this was studied by Samson many years ago. Actually, they study also a parabolic flow associated with this elliptic functional, and the critical points satisfy the equation. This tau is called torsion of phi equal to 0, which the trace of the nabla d phi. So there is a link between harmonic maps and the minimal hypersurfaces. When we take ambient space m bar n plus 1, a Riemann manifold, and we fix a hypersurface mn in this ambient space, then it is well known that the hypersurface is minimal if and only if the canonical inclusion map is a harmonic map. So we have this relationship between harmonic maps and minimal hypersurfaces. So you can consider also the biharmonic maps. So now you have the same map between Riemann manifolds, but now you consider the energy which is the integral of the tau phi square. So you get the put inside the functional the equation, the tau phi from the critical points of the previous functional. Then you have the bi-energy functional. This is E2 phi. So the critical points of the bi-energy satisfies the tau 2 phi equal to 0. This is called sometimes a bitension field. And the critical points of the bitension satisfy the functional tau 2 phi equal to 0, where tau 2 phi is the Laplacian of tau plus some curvature. I suppose that should be the curvature of M. There is a typo here. So, inspired by the case of minimal hypersurface, we say that hypersurface in the ambient space is biharmonic if the canonical inclusion is a biharmonic map. So, I have a canonical inclusion from hypersurface to ambient space, and if this inclusion is biharmonic, then we call it a biharmonic hypersurface. Clearly, every minimal hypersurface is biharmonic, because tau equal to 0, then you get tau 2 equal to 0. So I'll try to very quickly tell some previous results on the basic results. Actually, I'm not completely I don't know too much about this theory, but I'm learning, and but there are some basic results. There is a conjecture about in Euclidean space that any biharmonic hypersurface in Euclidean space is minimal. So we have many results that support this conjecture, chain conjecture. I'll tell you some results, not so many, just some. From Jiang chain, if in the case of a surface in R3, any biharmonic surface in R3 is minimal. Another interesting result from Nakauchi Urakawa, more recent result. If you have an ambient space with non-positive sectional curvature, then any complete biharmonic hypersurface satisfying that the integral of h square is finite must be a minimal hypersurface. Also, a very interesting result from Akutagawa Maeda, also a recent result, that any proper biharmonic hypersurface and properly immersed, because proper sometimes used in another context, but a properly immersed hypersurface must be minimal. There are many other results, but I think that these three results tell us that from the point of view of studying new examples and obtain classification results for basic examples, we should consider ambient space which have a positive curvature. So the natural place to start looking for new examples, or non-trivial examples of biharmonic hypersurfaces, is the unit Euclidean sphere. So there is a classical example, the small hypersphere, which is defined by you take x and you fix the second coordinate, and you get this small hypersphere inside the Sn+1. So it turns out that this is a non-minimal biharmonic hypersurface in Sn+1. It is a basic example. So we have new examples of non-minimal hypersurfaces which are biharmonic in the sphere. We also have another basic example, which is the generalized Clifford torus, which is the product of two spheres of radius 1/√2. But we have to be careful because the K cannot be n/2, otherwise it's minimal. So we want non-minimal examples of biharmonic hypersurfaces. So now we have this basic these two examples: the small hypersphere and the generalized Clifford torus. So there is a conjecture. Actually, there is more than one conjecture about biharmonic maps in sphere, but there is a conjecture of Balmuş Montaldo-Oniciuc, who is here, and which says that a non-minimal biharmonic hypersurface in the sphere must be an open part of the small hypersphere or of a generalized Clifford torus. So this conjecture says that the previous examples of non-trivial biharmonic hypersurface in the sphere are in fact all the examples. So there is in dimension 3 for surfaces. This was proved by Matheus Montaldo-Oniciuc. If you have a compact non-minimal biharmonic surface in S3, then it is the small hypersphere. We also have a result from Balmuş Montaldo-Oniciuc in the case of hypersurfaces with constant mean curvature, non-minimal, and non-negative sectional curvature. The result says that if you have a compact biharmonic hypersurface with these conditions, then it is either it is the small hypersphere or it is the generalized Clifford torus. So it confirms the conjecture in the case of hypersurfaces, which have the additional hypothesis of constant mean curvature and non-negative sectional curvature. Another interesting result, actually this result will be used in the proof of the result. I will apply this result of César, which says that if you have a compact biharmonic hypersurface in the sphere with constant mean curvature, a non-minimal hypersurface, then the mean curvature, the norm of the mean curvature is less or equal than n, and equality holds if and only if it is the small hypersphere. Let me take the opportunity to recall also some result of Simons and Chen do Carmo, Kobayashi, and Lawson. So Simons obtained a wonderful equation for Laplacian of second fundamental form, and then he proved that if you have a compact minimal hypersurface in the sphere with the second fundamental form satisfying bounded by a center constant, then you have some rigidity. Either it is flat or the second fundamental form is equal to n squared. No? Second fundamental form square equal to n. Then later, Chemo do Carmo, not later, 1 year after, Chemo do Carmo, Kobayashi, and Lawson independently proved, classified all hypersurfaces in the sphere which are minimal and for which the second fundamental form is equal to that constant of the Simon's estimate. So there is I think, a very interesting open problem to also well-known open problem to classify hypersurfaces in a sphere for which are biharmonic and which the second fundamental form square is equal to n. I think still open for biharmonic hypersurfaces. Okay. Okay, but if you notice the two basic examples, which are Clifford-Torrey, does the previous conjecture?
There's a question by Emilio if the previous conjecture would solve this open problem, right? If the previous conjecture were true, then would it solve this open problem?
I never thought about this, but I suppose maybe Cesar can help.
Maybe, of course, the conjecture is stronger than this. This open problem could be seen as an intermediate state, and maybe Matheus wanted to say classify CMC biharmonic hypersurfaces in spheres of normal phase square equal to n, not compact, but CMC, because CMC and normal phase square equal to n implies biharmonic. So we have a generalization of kind of generalization of do Carmo result because we passed from H0 to CMC. From minimal to CMC, keeping the square of the norm. So if you prove this will be just an intermediate step to prove that to prove the conjecture.
Okay, thank you, Cesar, for the help. Very lucky to have an expert on this topic here. Okay. So let us continue. So we have the two basic examples, which are recalling the basic examples is the Clifford-Torrey, which are this SK 1 over square 2 times Sn less minus K, and with K different of n over 2. So this Clifford-Torrey does not lie in a hemisphere. So we could ask if biharmonic hypersurfaces in hemisphere must be the generalized, the smaller hypersphere. So we can prove, we can give an answer to the question in the case of a condition on the mean curvature. So let Mn be a compact hypersurface in a closed hemisphere of Sn plus 1. If the n squared less minus h squared does not change sign, then either Mn is the equator of hemisphere or it is the small hypersphere. let's give some remarks. So the condition of the second fundamental form, h squared less or equal than n, implies that n squared less minus h squared is greater or equal than 0. So in particular, if the fundamental form is bounded by this square root of n, the conclusion is true. Also, when the mean curvature is constant, we have this condition. This follows from an equation in the next page, from the composition of the bitension field. So in particular, we have these two situations where the result is true. Okay, next page. Okay, let us now fix the notations and conventions of the work, because now we have some calculations. So we take the Laplacian, the analyst Laplacian, just the trace of the Hessian. The second fundamental form as usual, and the mean curvature is not normalized, just the trace of the second fundamental form, and without normalization. And notation also, because many equations in the next slides. So Nabla-Levi-Civita connection of hypersurface, Laplacian of hypersurface without a bar is just delta, and the Nabla with a bar, the Levi-Civita connection of ambient space, and the Ricci curvature of ambient space with a bar. So geometric quantities of ambient space have a bar. Okay. So this is the composition of a bitension field. If you have a Riemannian manifold and the hypersurface in this ambient space, then the hypersurface is biharmonic if and only if the normal and the tangent parts of the bitension vanish. Caesar studied for sphere and codimension, and then O applied also for hypersurfaces. This is a basic result in this theory. So our method to prove the main theorem is different from previous approaches. We find a formula for B Laplacian of a function defined on ambient space. Then after finding this formula, the results follows easily. Not an easy formula, however. If you have just a moment. If you have a function on ambient space, you can see the formula. I'm not sure. Maybe in my screen I cannot see the end of the formula here.
We can see the end is bnn minus bt.
Okay, then okay. So this formula relates the Laplacian of the restriction, the B Laplacian of the restriction of a function with the geometry of the ambient space. Actually, this formula has 11 terms, but we can group some terms in the Bn and Bt, so we get only in the case of a biharmonic hypersurface, we only get the first 5 terms on the hand right side, so we can study more easily. Then when we use integration, we only get 4 terms, because the two Laplacian the Laplacian goes away and the Laplacian also goes away. So it's something that we can study. An expression with only 4 terms is something we can study. Okay, so let me give an idea of the proof. So the proofs start with a very basic lemma. I think this is well known to many people in studying hypersurfaces. I'm not sure, but I include a proof also for convenience of the reader. So this formula relates the Hessian of a function defined on the ambient space with the Hessian of the restriction of this function. The connection is made by the second fundamental form. The proof is very easy. So we take a autonomous frame for which the connection of the hypersurfaces vanish at a fixed point, and then at this point the Hessian is just the derivative here. Sorry. And then on the ambient space, since the tangent part of the connection vanishes, we only get the normal part, which is exactly the second fundamental form. So when we put these two equations together, we obtain the lemma. Very simple and interesting result, this lemma. Okay, but then we have, we take the trace of that lemma and we get this equation, which is often used for studying minimal hypersurfaces. But then the idea is to take the Laplacian of the expression above. Okay, so the first term on the right-hand side is on the Laplacian, and the second term we get 3 terms. H times the Laplacian of nabla f n, then 2 times the mixed gradients, and then nabla f n times the Laplacian of h. It turns out that a lot of geometry is hidden in the term delta nabla f n. So we will study this term with more careful. Then we have to take 2 derivatives, but first we take only 1 derivative. And when we take a derivative of nabla f n, we get the Hessian of f minus the second fundamental form. Okay, but we have to take another derivative. So take a look on the expression on the right-hand side. You have a Hessian of f, and you have second fundamental form. And you want to change position of indices in the Hessian of f. Then you use Ricci equation, and you want to change position of indices in the second fundamental form. Then you use Codazzi equation. But you also have the second fundamental form EI and the Hessian of f again inside the second fundamental form. So you have to apply the lemma. So you do the following, the ideal proof. As I was saying, you take another derivative. For this first term on the right-hand side, you use Ricci equation, which is essentially Bochner formula, but not exactly, almost Bochner formula. Then from the second term, you use Codazzi equation. And then the second term also has another term inside it, and you use the lemma again. So you have 11 terms formula, a difficult formula, but it turns out that you can do very careful calculations and organize it to obtain the result. This is the ideal proof. Okay, now let us prove the main theorem. Since hypersurface is biharmonic, we have Bn equal to 0 and Bt equal to 0. I think for a moment I will go back just to show the formula. Okay, so this last term, Bn and Bt, goes away. We have left only 5 terms on the right-hand side. Okay. But then we can choose the function on the sphere, which is the x, the inner product of position vector and a fixed vector on Rn plus 2. It turns out that the equation of this function on the sphere is very well known. It is used to compute eigenvalues of Laplacian of sphere. The equation is well known. Then you take another derivative on the sphere and you get the expression for nabla f. So when you plug this function in the Laplacian formula, you get this simple expression, Laplacian f is equal to Laplacian trace of Haitian f, which I didn't write because it will not be used, less minus nh nabla fn plus h square f. Okay. Then you integrate this formula and you get only 2 terms, because Laplacian f goes away and the Laplacian of anything goes away since the hypersurface is compact, and we get only 2 terms on the right hand side. On the other hand, by that basic lemma, we also have Laplacian f equal to minus nf plus nabla fn h. Then if you take a look on this formula, if you multiply it by n and integrate, you can get a very interesting formula. Then you get is 0 equal to minus n square f plus nh nabla fn. But then you can add these 2 equations, integral equations. The term nh nabla fn cancels, and you are left only with the integral of n square minus h square f. Okay, then now the hypothesis, since the hypersurface lies in closed hemisphere, we can find a vector. This is now geometry. Since the hypersurface lies in a hemisphere, you can find a vector for which it lies in one side of a certain hyperplane passing through the origin. So you can find a vector v in Rn plus 2 such that xv is non-negative on M. Okay, but now we have integral of n squared minus h squared, which we assume we assume that does not change sign, and f is non-negative. So this quantity must be 0. Now, to conclude the proof, we use a classification result, which I mentioned from Caesar, but I'm not sure now. Okay, but now I cite this paper, Balmuş Montaldo-Oniciuc, 2008, and we also use a unique continuation property for Biharmonic maps. This is a new result of Branding Oniciuc, 2019. Okay, another application. Let x be position vector of ambient space of Rn plus 2 and take a canonical basis. Then Takahashi proved that hypersurfacing sphere is minimal if and only if Laplacian xi equal to minus nxi. So we can apply the formula to have a similar result for Biharmonic hypersurfaces. So hypersurfacing spheres Biharmonic if and only if the Laplacian of xi equal to n squared plus a squared xi minus 2 times nh and I. This result written different but equivalent in Montaldo-Oniciuc. Okay, now maybe I want to say some problems that can be studied. So maybe we can find another f bar. No, so now we have this Laplacian formula. So we can maybe find another function on sphere to obtain a different result. So we found a f bar to characterize a small hypersphere. Maybe we can find f bar, maybe, I don't know, to characterize non-minimal Biharmonic Clifford tori. I think another interesting problem would be to find good application of the Laplacian formula to biconservative hypersurfaces when only the tangent part of the bitension vanishes. So this would also be interesting, maybe. Also, extended the Laplacian formula to submanifolds. I don't think this is very easy. I'm not. But it would be very interesting. Okay. The paper is on archive, Biharmonic hypersurfaces in hemispheres. So what time I have?
I guess you still have 10 minutes.
10 minutes?
But we can go to questions if you want.
I don't know. I read something here that maybe if left some time I would show. Otherwise, I didn't show.
Right, do show.
Can I show it?
Absolutely.
Okay. I want to show you an alternative proof of main theorem is not, which I did not include it in paper, but maybe it's a flexible idea that can be applied to other situation. We have another proof of main theorem. I say I'm not including paper, but so this idea comes from I don't know, maybe it should be very old, but I learned in paper from Tiger coding. So you write the metric as a warped product. Then, if you take f bar equals to the integral of the warping function, you get a function which diagonalizes the Hessian of function. The very general result for any Wapak product, you can do this idea. So now you have a function which diagonalizes the Hessian of f bar. Now you can compute also the third derivative of this function. So let me recall you that bar means that it's on the ambient space, which is the sphere, Sn plus 1. So you have this. Now, as before, you get this formula for the Laplacian, and you get the next formula for Laplacian of f. Then you integrate these formulas, multiply by n, and again, you obtain the integral of h squared minus n squared times f equals to 0. But now the condition that m lies in a hypersphere, I didn't explain, sorry, r is the distance function, intrinsic distance function of the sphere from a certain fixed point. So the condition that this hypersurface lies in hypersphere means that r is in fact the angle, right? So it means that r lies between 0 and pi over 2. But this means that the function f is non-negative since it is cosine of r. So as before, you get equality h squared minus n squared times f equal to 0, and the rest of the proof is similar. So maybe this idea has other applications. I want to show you this. Okay, now I finished. Thank you.
Okay, thank you. Have we got any questions for Matheus? Well, I do. So let me just, if you came in late, let me just remind you that if you want to subscribe to our mailing list or check our previously recorded talks, you can find the instructions on the chat. But okay, Matheus, so this is not immediately about your theorem because I mean I'm not familiar at all with biharmonic maps, but I know in the case of harmonic maps, certainly maps involving spheres admit you can in various cases generalize results about maps involving spheres to maps involving just any homogeneous manifold, you know, because one really is using the fact that the spheres are homogeneous spaces, so they have some special tuples of vector fields, right, with potentially divergence free, so they can use them to make computations easier and so on, right? So, yes. So there's not, in some sense, there isn't much special about spheres as much as harmonic maps are concerned, because if you think about spheres in terms of their homogeneous structure. So I was thinking, how much of that would still be true in the biharmonic context? Can you, do you have methods that really rely on the sphere as, say, something of, I mean, is the sphere really there, or because there's something spheric about it, or is it just there as essentially a homogeneous space? Especially in the motivating results, right? So in the opening of the talk, presents lots.
Yes. Now that you mention, I just know one paper, maybe two, that did this that you comment, but not for biharmonic maps. I know in Yang-Mills theory, paper of Max Tan, which generalized the index estimates instability estimates of Yang-Mills connections over the sphere for two homogeneous spaces, and I think maybe it's possible. I don't know, but it's an interesting question. Maybe Cesar may know something about it, but the point here is that we are using the functions from ambient space which are very explicit for the sphere, but maybe it's possible to do something for homogeneous space. I'm not sure. Maybe
do your functions have some symmetries, right? Because I mean they do have these radial symmetries.
Yes.
So maybe you could have a sort of left invariant version of these functions. I don't know. I don't have any intuition about a biharmonic map. But in the realm of harmonic maps, I find that more often than not, when people working on spheres, they're really working on spheres as homogeneous spaces. So maybe you could just have a look at this from this perspective. You want to use the fact that on the sphere you have a privileged set of vector fields with a very non-trivial property. But those guys, which simplify computations and allow you to these vector fields, they also exist on homogeneous spaces. They're not intrinsically spherical in any way. So whenever your proof just depends on writing things in terms of the right vector fields, it also should be generalized to homogeneous space. But again, I'm completely ignorant about biharmonic maps, so maybe I'm not making any sense at all. Maybe if Eric is there, he can comment on this, or maybe not. But yeah.
I'm not sure. I would also like to hear about it if somebody has some information. Don't know. Okay, have we got any other questions or comments for Matheus?
I have a question.
Go ahead.
Yeah. The homogeneous spaces have a warp of metric. Kind of metric in this last proof. Do you know, or anyone knows?
I didn't understand very much.
I think your audio is a bit weak.
Okay. Now, if for homogeneous spaces, are there a warp of metric, as in the last proof?
Homogeneous space?
Maybe can you type the question, Luis, because it's really hard to hear you.
Thank you.
Yeah, maybe if Luis can type the question on the chat.
Okay.
Because it's getting a bit hard to get his mic. Do you homogeneous have warped metric?
I think not in general. No, I don't think so. I was actually the last proof. I was thinking about application in complex hyperbolic space, but it didn't work. But because complex hyperbolic space has double warped metric, not warped, but double warped, and I was trying to make an application in the CPN, but it didn't work out.
Okay.
Okay.
Any more questions or comments? Well, if not, then Paulo, do you want to?
No, thanks. I'm fine.
All right. Okay. So let's thank Matheus again, please.